Before am I audible?
Yes.
Yeah. Before I start my talk, I would like to thank the organizers for very kindly inviting me for this beautiful workshop. It's always fun to visit Brazil. It's almost like India, but with less crowd. The food is as good as we have in India. So I was told by Jose that I should feel free to embarrass his former thesis advisor. Uh, so I have not had the pleasure of working with Professor Miranda, but I would like to thank you for all the contributions you have made, um, especially for this legion of very, very impressive graduate students that you have produced, and amazing work that you have done over the past so many years. In fact, this work actually is crucially centered around the work by yourself and Professor Dobrosolovic. So with that in mind, let's start my talk. So my talk is titled A Cloaked Griffiths Phase in Low Dimensional Superconductors. The cloaking is from Star Trek, the wrong universe. Star Trek, where you have these Klingons, the battleships being cloaked, right? So, yeah, but yeah, but I prefer Star Trek. So that I like things much more, not so magical. Okay, so this talk is based on a set of experiments that were done in India by in the group of Professor Avik Bede, and so Simran is the person who did all the very nice experiments. So this is a collaboration between Avik, myself, and Thomas, and a host of others. So let's see what this project is all about. So the sort of physics problem that I'm interested in is to understand quantum phase transitions in the presence of disorder. And the sort of quantum phase transition that I'm interested in at this time is to look at a field-controlled or field-tuned quantum critical point in a disordered superconductor. So the standard approach to this is to actually derive what is called the Landau-Ginzburg-Wilson theory. And this Landau-Ginzburg-Wilson theory can be derived by starting out from a microscopic Hamiltonian, constraining the fermionic degrees of freedom to a Hubbard-Stratonovich field, which I call in this case to be phi. So this is gone, I think. Can I use this? Yeah. So phi is a Hubbard-Stratonovich field, which is a superconducting order parameter in this case. And the idea is that you integrate out the fermions. Of course, many of us know that this is not a very straightforward process, and there are issues with this. But let's assume that one can go ahead and do this. And so what you do is you effectively derive a phi-4 type model, where the phi-4 type model effectively lives in d plus z dimensions. Correct? The distance to criticality for this model is essentially encoded in this delta naught. So for example, if you can think of something which is field-tuned, this delta naught is effectively how far you are away from the critical point BC. So it's some sort of a non-thermal tuning parameter that actually encodes the quantum phase transition. The other important point over here is this mod omega. This mod omega is what is called the Landau damping. It provides the damping to the order parameter degrees of freedom. So that is what comes out of integrating out the fermions. So it's the fermions that live around the Fermi surface that actually gives you this mod omega. What is going to be very important for our talk is the fact that this mod omega, in terms of imaginary time, can be Fourier transformed and looks like a 1 over r square interaction or 1 over tau square interaction in imaginary time. So the sort of models, sort of things that I'm interested in is to look at the superconductor normal state transition as a function of an applied field. And this is the sort of experiment that was done on Lascaux films that were grown on the strontium titanate substrate. So these are 2D superconducting transitions that are field tuned, and the question that we are going to ask is, what's the critical behavior in this? Yeah? Yeah, yeah. So there are vortices, and there's this movement of the vortices and things like that. So, yeah. but I'm interested more in the sort of critical behavior that comes out of this transition. Okay. I will speak a bit more about the about the inset in a few slides from now. So let's go on. So if you're given a model like this, and if you are trained the way I have been trained, the first thing you would have done is to try to do an epsilon expansion. So sorry. Oh, I should go back. Sorry. Okay. So the question that I'm trying to ask is, you have a critical point. What is the effect of disorder on this critical point, right? So what sort of critical behavior would one expect from this? And the first thing that one would do if you were given a problem like this was to do renormalization group, momentum shell, or what. As a theorist, that's a dream thing to do. And if you do this, then you find extremely interesting behavior. And what you find is that you find runaway flows to large disorder strength. So you have no way of encoding the transition and getting the critical exponents out in such a theory. Okay. So now that was the state of being very much until say 2005 or so, when two people in this audience, that is Thomas and Jose, came up with a very novel way of actually dealing with this problem. So to get around this concept of runaway flow and so on and so forth, what they did is try to do a variation of the real space renormalization group, or the real space renormalization group based strong disorder RG that was actually first invented by Dasgupta Mahu and then later refined by Daniel Fisher in the study of transverse field Ising models in the presence of disorder. Okay, so if you do this, then what happens is, what they did is they used a discretized version of this large N theory, where they effectively, they generalized the phi-4 model to a large N theory and then discretized it, and then the sort of RG they did was an RG that essentially looks at local energy scales and compares and competes local energy scales with respect to each other. For example, in this model that we have, there is an epsilon I, which is some sort of renormalized distance to criticality, and this epsilon I essentially competes with this Ji, which actually forces rotors or order parameters on two sides to actually lock onto each other. So the two competing scales in this problem are epsilon I, which is a local distance to criticality, and this Ji, which forces the rotors or order parameters on two, say, think of this as Josephson junctions, of two Josephson junctions to near neighbor Josephson junction to face lock. Okay, so now what we do is we essentially use this concept to actually go ahead and do the RG, and this was done very quickly. Sorry, this actually is not my fault. I can use the keyboard. Thank you. Okay. So let's look at it very quickly. I mean, I can't go through the SDRG process in these lectures, but let's look at what the SDRG entails. So what the SDRG entails is you go through your chain of Josephson junctions, and you figure out what's the largest energy scale. In this case, suppose the largest energy scale is an on-site distance to criticality. Let's call that epsilon 3. So what you do is you actually integrate out that degree of freedom. So you integrate that degree of freedom out, and what that does is it then generates a weak coupling between the initially unconnected sites. So this weak coupling, the weak coupling is this object called J twiddle, and this has the sort of recursion relation, which is J2 J3 by epsilon 3, with the large energy scale epsilon 3 coming in the denominator, and that's actually good for us, right? So in the same way that you have decimated or removed a site by using this RG, the other option for us to do would be what would happen if the largest energy scale was a J. the coupling between two nearest neighbor junctions. Yeah, sure. Yeah, so that's completely correct. So so you can in principle apply this technique to higher dimensions, but you have to be careful when you do that because you change the topology of this whole thing. But the general idea or the general philosophy is that the same sort of critical behavior holds. With Z? Yeah, so okay, so there are two Z's that are there in the problem. So there is a Z, which is a dynamical exponent you start out with, which is pegged at 2. But there is a non-universal dynamical exponent that comes in because of the disorder, and that we'll see in a minute. So for example, in the Griffiths phase, there is a dynamical exponent Z, which is non-universal. Okay, so here we have a bond dissemination. So we have the other regime where the largest energy scale is this coupling between the nearest neighbor Josephson junction. Let's call that a J2. And the same thing, what happens is you can actually integrate out. So the physics here is that when J2 is very, very large, the faces on these two sides, 2 and 3, gets face locked. And then what you can do is you can take that as a composite object, integrate that out, and essentially see to it that you have at a new site a new distance to criticality, which is renormalized downwards, once again with this large scale coming in the denominator, right? So effectively there seems to be a duality between the two recursion relations that we have now there seems to be a duality between the two recursion relations that we have now derived, and this recursion relation is actually important. Sorry, this duality is actually important, but we won't go into this. So if you look at these recursion relations that we have derived, these recursion relations are exactly of the same functional form as that was derived by Daniel Fisher for the case of the transverse field Ising model. In that transverse field, so all his results will effectively carry over. In effect, what he has shown is that the sort of critical behavior you get for this problem, that is the superconductor normal transition in the presence of disorder, or for the random transverse field Ising model, has very different sort of critical behavior. And how is it different? So you know that when you come close to a critical point, there are things like the correlation length, which diverges as a power law. Associated with this correlation length, there is a correlation time, which also diverges like a power law in conventional transitions. So that means this psi tau goes as psi to the power z. However, in this case of transitions, which are what are called as infinite disorder transitions, the form of the scaling changes. In particular, what you find is that the log of the correlation time essentially goes as a power law and not the correlation time going as a power law. So there is a difference. There is an activated scaling that comes into play, and this activated scaling essentially gives you some very interesting physics that we'll see very soon. So let me rephrase. So you can really sit down and show that for this sort of set of models, Harris criterion is violated. When you see that the Harris criterion is violated, that means that you have to flow it to a new fixed point. But what is a new fixed point like? So what Thomas and Jose have actually shown us is that the new fixed point is of a very particular kind, and that particular kind of fixed point is what is called as infinite randomness fixed point. Okay, so we have done some work along with these two gentlemen, where we have considered other forms of dissipation, okay, like superomic and so on and so forth. So are there any questions so far? Okay, let's go on. Because of the consequence of this, because of the consequence of having an infinite randomness fixed point that is controlled by this distance to criticality delta naught, what can also show is away from the critical point, the correlation time essentially diverges encoded by an exponent 1/2 delta naught. Now this delta naught, as you remember, is somehow related to the distance to criticality, so that effectively means that this object, this 1/2 delta naught, will change as you are away from the critical point. That means when you are in the phase, this 1/2 delta naught will change. That means you have a non-universal Z. That means that if you are looking for some effects of or unconventional effects of disorder, then one of the smoking gun signatures that you would like to look at is to get a non-universal Z dependence. So this is the other exponent that I was talking about. So what we are going to look at is to look for a dynamical exponent Z, which actually diverges as we approach the transition. Okay, that's what I'm trying to do. So to do so, let us just briefly understand what sort of physics is it, what is the underlying physics or the pretty picture that one can think of when you look at this infinite randomness physics, this what is called as the Griffiths phase physics, and so on and so forth. So essentially, all these beautiful results that Thomas and Jose and maybe their collaborators came up with has a very nice underpinning to it. And the nice underpinning to it is related to the effects of what are called rare regions. So what are these rare regions? These are regions which are locally ordered, okay, even though the bulk is in the disordered phase. So you have locally ordered, so if you think of in terms of magnets, so you can think of locally ordered magnetic regions in a bulk which is completely disordered. And it's the dynamics of these rare regions that actually produce these Griffiths effects, or these non-universal dynamical exponents, for instance. So let's go back and try to figure this out in a bit more detail. Okay, so these rare regions have a finite extent in space, right? But due to the fact that you are in a quantum phase transition, they have effectively an infinite range or infinite dimensionality, or of infinite dimensionality as you go to t equal to 0. So think of like infinitely long rods that are there and which have some dynamics. But because these things are infinitely long, they have a very slow dynamics by themselves. They move very, very slowly. And it's this very slow movement of these objects, or the dynamics of these very long elongated objects, that actually gives you this non-universal anomalous behavior. So the important question that Thomas essentially answered was, each of these rare regions has a dimensionality, and now if the dimensionality of this rare region is equal to the lower critical dimension, that is the dimension below which, or at and below which you lose long range order, then effectively what happens is each of these regions essentially tunnel very, very slowly, and you get quantum Griffiths phase. But you can ask the following questions. What would happen? What would happen if each of these regions can by themselves order? Okay, so such a situation would have happened, for instance, if you take an Ising model and you have a 1/r² interaction in the Ising model. The 1/r² interaction in the Ising model, as many of you students would know, is exactly the sort of range that you need for an individual Ising model to order. So if one of these rare regions order, then it orders and it does whatever it does by itself. Then at some other place something else orders, and at some other point something else orders, and then you should get a loss of homogeneous order and a smearing of transition. Okay, so the crucial input parameter over here is what is the dimensionality of the rare region, and how does it compare to the lower critical dimension of the system. Okay, so that's going to be important. So let's go back to this very nice experiment that Avik and Simran have done. And so if you look at this essentially plots the sheet resistance as a function of the applied magnetic field. Immediately you see something very, very interesting over here. Oh, sorry. Immediately you see something very, very interesting over here. If you blow up the crossing the region where the curves cross, then it's very, very clear that the crossings don't happen at a single point. That means the BC keeps walking or shifting away. This is actually something that was seen in other experiments. on indium oxide films that, that was done in around 2019. And Thomas and his collaborators essentially encoded this crossing or explained this crossing by saying that these crossings are due to the leading irrelevant operator. So see, if it's a transition from a superconducting state to a normal state as a function of some BC, as a function of some magnetic field, then there should be just one crossing. But the inset shows many crossing, right? And the question is, why is that? Why is there so many? Why is this behavior? And this was essentially shown by in this paper that this variation in the crossings essentially comes because of having a leading irrelevant operator, and that the effect of the leading irrelevant operator essentially goes to 0 at T equal to 0. Okay, capital T, the temperature to 0. So now that we have understood why there are these multiple crossings, let us try to use let us use a strategy to extract mu z. So what we are going to do is we are going to essentially use a power law scaling ansatz to actually evaluate the exponent mu z. So it's very clear that what I'm trying to do is I'm trying to parameterize my nu z or an effective nu z in terms of its variation with respect to temperature. So if this nu z, as I'll show you in a slide from now, if this nu z happens to be universal, then there's no unconventional physics that is driven by disorder. Whereas if this nu z varies with the applied magnetic field, then there is some sort of Griffiths behavior. Okay. So our strategy to essentially glean out nu z or effective nu z follows the following procedure. What we do is we take magnetoresistance isotherms, three nearest one of them, and essentially try to figure out where the critical BC and RC lies. Taking these three isotherms together, we essentially try to do a scaling plot, scaling based on this power law scaling ansatz. This power law scaling ansatz effectively it tells you what nu z is as a function of temperature. Okay, so that's what I'm trying to do. This is standard trick. So if I do this, then what I see is I can derive nu z as a function of t, and I can derive effective nu z as a function of t, or I can also derive nu z as a function of how far you are away from the critical point. So if you do that, what you see is that the nu z has a kink-like feature. So for all temperatures that are less than, say, 0.07 Kelvin or so, what you see is that nu z as a function of the magnetic field actually goes through a divergence, exactly as one would expect for the Griffiths physics. Okay, and in this regime, if you look at the temperature dependence of this effective nu z, then it exactly matches to what one would expect by the infinite randomness fixed point scenario. Okay, so everything looks hunky-dory, everything looks exactly as what one would predict it to be. Okay, so this is exactly what was found in another set of papers by the group of Alan Goldman and earlier, and this divergence exactly matches the predictions of Thomas and Jose. But now comes the interesting part. If you come lower in temperature, then effectively what you can see is that the nu z effective moves away from this nice 1/log, which is what you would expect, to a power law. And one can show that this power law behavior is actually incompatible with the notion of a quantum critical point. It's too stark a divergence. Okay, so another way to figure out that there is something going wrong over here is that you can essentially match or take your data and essentially plot it on a scaling collapse with respect to this activated scaling scenario. So for all temperatures that are above 0.07 Kelvin or so, everything maps on to these two critical isotherms. But on the other hand, for temperatures below 0.07 Kelvin, you don't see any data collapse. So something goes wrong, something should go wrong as you reduce in temperature, or there should be some other mechanism that destabilizes the infinite randomness fixed point that one expects in such systems. Okay, so so we don't really know what that thing is, but here is a possibility. So our explanation hinges on a very beautiful paper of PRL some time ago by Vlad and Professor Miranda, and the effective idea is the following. So when you're going through a phase transition, as you said, in the presence of disorder, there are these rare regions, correct? And these are non-interacting. So the usual Griffiths physics is that of non-interacting rare regions, right? Now the sort of questions that these gentlemen asked was, you mean I made a spelling error? Yeah, I am so sorry. Yeah, I'm so sorry. I'm so sorry, but yeah. Okay, so it's actually Professor Dobrosolovic who is there. So, so what I have is that I have rare regions, and these rare regions are actually interacting with each other by some sort of random long-range interactions, say, for example, RKKY. So these RKKY interactions actually couple these rare regions together, and the question that one would like to ask is, what is the effect of such long-range random interactions? And this was worked out in detail in their PRL. So effectively what they do is they say that these rare regions are essentially held far apart, but they're randomly placed. That means that this object Jij over here is a random variable, and what they did is they decided that the sort of physics that one should wonder in this case is having a bunch of rare regions all interacting via their RKKY interactions, but these RKKY interactions now, so each of them each of the rare region is a droplet, and so that's the SRR, and then there's this RKKY which is random. So they did a replica trick that effectively allowed us to integrate out this interaction between the rare regions at site I and j, for instance. Once you do that, you evaluated effectively this object by means of a saddle point evaluation. Yeah, they evaluated this by means of a saddle point, and out of this evaluation, essentially, so this is where the disorder comes into play in terms of some sort of a local susceptibility. And if you want to look at this local susceptibility, then what happens is, just a minute. If you want to look at this local susceptibility, or you want to evaluate this local susceptibility, then you want to have some information about the density of states, and this density of states gives you some information about the random distance to criticality on each of these rare regions. So the infinite randomness fixed point and the attendant Griffiths phase essentially tells you that in the Griffiths phase, the density of states of the distribution of local gaps has to have this power law behavior. If you sit down and actually evaluate the integral and putting this mod omega as a cutoff, what it tells you is that the RKKY interaction essentially produces an additional source of damping. This additional source of damping comes in and changes the mod omega or the lambda of dissipation. It actually makes it's slower. So effectively what happens is that the rare regions that are there on each of these sites now sees a much stronger dissipation, this much slower dissipation. This much slower dissipation in turn forces the rare regions to start ordering by themselves, because the rare region goes below its lower critical dimension. So at each of these sites, it starts ordering by itself. So effectively what happens is there is a smearing of the transition. And the cutoff, that means as you lower in temperature, this mechanism starts acting. You cut off the Griffiths phase, and then you move into a regime where the transition is actually smeared by the combined effects of disorder and these long-range interactions. So that's a sort of idea we have, that effectively what happens is that long-range interactions effectively come in to give you another source of dissipation. This another source of dissipation essentially ends up smearing the infinite randomness fixed point. Okay, and so what happens? What happens over here is each of these regions essentially phase locks. They sit there, and then there is a tunneling of the Cooper pairs from one to the other, and that's probably what gives an anomalous metal phase in these models. This is just I just threw it out there. So each of these Josephson junctions essentially undergoes a transition by itself. It goes to smearing, and this smearing can be actually seen if you map out the BC versus temperature phase diagram. At low temperatures, you see a tail, and this tail may be because of smearing, but unfortunately, even for the Griffiths phase, I think there is a tail. So each star region orders by itself, and there's a strange metal phase due to correlated hopping of Cooper pairs. So is it time for me to?
You have 3 more minutes.
Okay. So the open questions are and conclusions are, so the Griffiths phase is destroyed by this additional source of dissipation that comes from this long-range RKKY type mechanism. So once it is smeared, or sorry, once the Griffiths phase is destroyed, what does the ground state look like, right? So what is the nature of the ground state? We don't know. The question that I have in mind is, how generic is this mechanism that I've been talking about, right? For example, the earlier works that were done by, that I quoted, whether if you go to low enough temperatures, you still see the smearing, or is it something very generic, very specialized to the sort of materials that we are dealing with? The question, and okay, technical question that I want to ask, especially people here who are very much experts in this, is the work by Dobrosolovich and Miranda essentially dealt with this model in some sort of an approximation, which is a saddle point approximation, using this cavity method, right? The question that I have is there a better way that one could capture this sort of smearing, or this sort of cutoff of the quantum Griffiths phase by doing a real proper SDRG, by keeping in the long-range interactions in play? I don't know. Okay, so in the last minute or so, so some of the things that we have been working on, but would have loved to talk about all of these things, is we are working on some metal insulator transition with spin resolved disorder. With Thomas and company, I've been working on some Higgs localization. So there's a poster on this, which is on Thursday, right? So then we are working on clock models and disorder. Also, a huge amount of disorder-driven physics. Okay, so I would love to talk about these things to all of you, if I could. So thank you for your time. And
thanks, Raj, for this disorderful talk. Questions?
Yeah, this is it's very interesting, and thank you for talking about our work, which I have already forgotten about. But yeah, that's something that I always thought maybe someday will become relevant. But one thing that caught my eye, if you can go back to the first experimental slide, I want to ask a question about experiments, which I'm confused about. Because in a standard, this superconducting films, you see a resistivity dropping either to 0 or it goes up. There is no curve that goes down to a finite value saturation like this. More recently, various people have advocated that this can happen, and this goes under the name failed superconductors, which is a big claim by Kivelson, Spivak, and their friends. Now, is this the theory? Do you think that this is the same phenomena they are talking about? Do you claim that what you are proposing is a theory for a failed superconductor, and do you think that these experiments are correct? I mean, I'm not talking about those necessarily, but all of those that...
So this failed superconductor anomalous metal, right? So this is the one where there is no temperature dependence. It saturates, exactly. So I am not saying that the theory that we have or that you guys have developed may be applicable to understand the anomalous metal, but the idea that we have is maybe what is happening is that each of these regions have phase locked, and then what you're seeing is some sort of correlated Cooper pair hopping. And that could be what is giving you this anomalous metal. The second thing is, for this theory to work, you need a metallic phase. You need a mod omega, right? Without a mod omega, you don't have this thing to work. And if this mod omega is not there, then you don't have Landau damping, and you don't get this physics that Jose and Thomas worked out. You will get physics of Raphael and Gil Raphael and Altman and company, right? Yeah. Gil Raphael. Raphael, sorry. I'm Indian. I'm allowed to pronounce it any way I want.
More questions? Everyone happy? So, Raj, I have a question to this thing which you had at the end. So, I mean, I guess your conclusion at the end was that the transition is smeared, right?
Yes.
But by the RKKY
Yes.
effect. But smeared transition in the sense that this thing always orders.
Always ordered.
But of course, which then means that if experimentally you increase the field even further, there must be other effects which eventually destroy superconductivity, which are not captured in your description.
Yes, I agree.
But then the transition in this regime would be of an entirely different nature.
I would think so.
Which is something which you did not
I have
think
not
about.
thought about this at all. Yeah.
Let me clarify maybe. So if it was a smear transition, let me try to clarify. So if it was a smear, is it on? If it was a smear transition, right, then there would be a tail, and that tail would reach out, well, up to some point, and how far out depends on microscopic details, right?
Yeah.
So it would not necessarily go all the way to infinity. That depends on how the disorder looks like microscopically. That's a non-universal property, right? And what happens at that point, again, is a non-universal question that depends on details.
So the Barrett disorder tells you where it ends. Right?
But large magnetic fields due to a superconductor is not captured anyway properly,
sure.
right?
Yes.
Yeah.
So, further questions? None at this point, so if more questions pop up, the speaker will be available at the coffee break.
Yes.
So with this, let's thank him again.